In this video, I will determine the symmetry of the vibration modes of a tetrahedral structure of a beryllium-4 atomic cluster. You can find this Excel spreadsheet in my webpage. It's over here. If you scroll down to building physical chemistry from scratch, you will find some Excel spreadsheets titled molecular symmetry. You will find this one as well, or you can simply search for PChemCW in any web browser and you'll find my webpage. Now let's look at the tetrahedral character table. This is the character table for the tetrahedral point group. We have a total of 24 different symmetry operations. First, identity symmetry operation, that means doing nothing, and then we have 8 C3 symmetry operations. Because in this tetrahedral structure we have a total of 4 C3 axes, each crossing one of the 4 atoms. And when we have one C3 rotational axis, there are 2 symmetry operations, because you can rotate the structure about that C3 axis 120 degrees or 240 degrees. That's why we have only 4 C3 axis but 8 symmetry operations here. And we have 3 C2 symmetry operations, 6 S4 symmetry operations. Over here, S sub 4, that means you rotate the structure 90 degrees followed by a reflection. And we have 6 sigma D symmetry operations. Why 6 of those? Well, you could just label the 4 atoms 1, 2, 3, and 4, and then you can have a sigma D that contains 2 out of the 4 atoms. For example, this symmetry plane may contain these 2 atoms, or this 2, or this 2, or this 2, or this 2, or this 2. And then we have 6 different sigma D symmetry planes, and each symmetry plane allows us to perform one symmetry operation. So that's why we have a total of 24 symmetry operations if we sum up this 5 numbers. And also we can determine the order of this character table or the tetrahedral point group by taking the squares of these 5 numbers under the identity operation. After we square this 5 numbers, we get 11499, and we sum up this 5 numbers, we also get 24. So the order of the tetrahedral point group is 24. Now let's look at the motions of these atoms. We have 4 atoms in this structure, and 4 atoms have 12 independent coordinates and therefore 12 independent motions. Among these 12 independent motions, we have 3 translations and 3 rotations of the entire structure. In 12 minus 3 minus 3, we will see 6 vibrational modes. And how do we determine the symmetry of the vibrational modes? First, we look at these 5 different types of symmetry operations and determine the number of atoms that remain in their original positions after this symmetry operation. If we do nothing, all 4 atoms remain in their original positions. If we do a C sub 3 rotational operation, only 1 atom stays in its original position. What if we do C2 or S4? All 4 atoms will have to move out of their original positions, so it's going to be 0 and 0. What about sigma D? Each sigma D contains 2 atoms, and these 2 atoms will remain in their original positions after this sigma D symmetry operation. That's why we have this 5 numbers. And now we find the characters of x, y, and z. It's here, so it's going to be 3, 0, -1, plus 1 over here. Now we multiply this 5 numbers and this 5 numbers correspondingly. We get 12, 0, 0, 0, 2. And then we multiply these 5 numbers with the order of the symmetry operations. It's in the first row, it's 1A3, 6, 6. So for example, 6D, we have sigma D, we have 6 sigma D operations. So after we multiply these 5 numbers with the 5 numbers in the first row, which are the numbers of the symmetry operations that belong to each type, we'll get this 5 numbers, 12, 0, 0, 0, 12. And now we multiply these 5 numbers with the 5 characters for each symmetry. We have A1 symmetry, A2 symmetry, and E means doubly degenerate. T means triply degenerate. So you can see for A1 the characters are 1, 1, 1, 1, 1. So we have these 5 numbers times 1, 1, 1, 1. And then let's look at A2. It's 1, 1, 1, minus 1, minus 1. So over here we have this 5 numbers times 1, 1, 1, minus 1, minus 1. We got this 5 numbers. Now E, doubly degenerate. Let's go up. We have 2, minus 1, 2, 0, 0. And then we go down. This is doubly degenerate. 2, minus 1, 2, 0, 0. So we have this number times 2, minus 1, times 2, times 0, times 0. And we have this 5 numbers. After we do this for each irreducible representation, we have this 5. We get 5 numbers for each row. We sum it up like this. We sum it up. We get 48 for this T2 irreducible representation, and then we get this 5 sums that correspond to this 5 irreducible representations or 5 different symmetries for the motions of those atoms, and then divided by the order of the point group, which is 24. This is also the number of different symmetry operations. So this divided by this, and then we get 1 and 1, 0, 1, 1, 2 over here. This is 48 minus 24. So we got these 5 numbers. What does that mean? That means simply we have one motion of those atoms correspond to A1 symmetry. 1 doubly degenerate, 1 T1 triply degenerate, and 2 T2 doubly degenerate. And we can sum it up. We have 1 here, and this is doubly degenerate. So plus 2, and then plus 3, plus 6. We get a total of 12. All right, 1 plus 2, that's 3. 3 plus 3, that's 6. 6 plus 6, that's 12. It's just because when we have 4 atoms, we have 12 independent motions. Now we need to subtract the rotations and translations. We have rotations here, T2 symmetry. That's, oh, I'm sorry, this is translation. And over here, this is rotation. When you see R sub X, R sub Y, R sub Z, those are the rotations about the X, Y, and Z axis. They belong to the T1 triply degenerate irreducible representation. X, Y, Z translation, they belong to T2 irreducible representation. So we need to minus a T1, we need to minus a T2. Again, this is to remove the rotational modes. This is to remove the translation modes. So in the end, if we are looking at just the vibrational modes, we have 1 A1 symmetry, 1 doubly degenerate E symmetry, and 1 triply degenerate T2 symmetry. And we can see 1 plus 2 plus 3, we have 6 vibrational modes. And then you can use some computational chemistry software to calculate the vibrational frequencies and intensities for a structure like this. What if you have another atom right at the center? Well, it's pretty easy, because when you do any symmetry operation, this central atom remains in its original position. So over here, the number of atoms that remain in original position. So if you have one additional central atom, you simply just add 1 to all these 5 numbers. So I'm going to show you the structure with a central atom, and then you can see this is 52113. 52113 compared to this 41002. 52113. So that you can see the difference here, and you just follow the same procedures, and in the end you will get the symmetry for the vibration modes. You will have one additional T2. The reason you have one additional T2 is because after you add the central atom, you get one additional rows here included in the sum here. Alright, and that's why you have one additional T2 symmetry for the vibrational modes. Again, if you just search for PCAM-CW in any web browser, you'll get to my web page, and over here, so PCAM-CW, and then you click this, you go to building physical chemistry from scratch. You'll see a lot of documents. One corresponds to a video, including the molecular symmetry. Those are Excel files. Let me know if you are interested in some other point groups, some other analysis using group theory. We use group theory for the analysis of vibrational modes, infrared Raman spectra. We use this to analyze molecular orbitals, atomic orbitals. In organic chemistry, and also in inorganic chemistry, transition metal chemistry.